In Neolithic, Bronze Age, and medieval Mesopotamia, the persistent problem with the soil has always been aridity and salinization. Mesopotamia is the river valley between the Tigris and Euphrates rivers, and it is an alluvial floodplain. That is, it's regularly inundated by the seasonal overflow of the rivers, which leaves behind lovely deposits of fresh silt and nutrients that make the soil fertile. Before the dawn of agriculture, wild wheat grew on these silty floodplains and was harvested by hunter-gatherers. When people began to farm, river waters were naturally the cornerstone of their treatment of the soil. Agriculture is impossible in arid regions like the Middle East without irrigation. Irrigation was the key to farming in Mesopotamia, and it was the bedrock of the Sumerian, Babylonian, Assyrian, Median, Achaemenid, Sasanian, Umayyad, and Abbasid empires. In order to combat soil aridity, the Sumerians were the first to build canals off of the Tigris and Euphrates, which diverted river water onto cultivated fields. One ancient source records the building of a canal regulator out of more than 600,000 mud bricks, an absolutely massive undertaking for the time. The use of such canals remained in practice well into the Islamic era. Really, irrigation can be considered the first and primary soil amendment in the Mesopotamian region. However, irrigation in arid environments is not always the best long-term solution to soil dryness. Irrigation frequently leads to salinization. The area between the Tigris and Euphrates rivers is a very flat plain. On the plain, there's a lot of groundwater close to the surface with little potential to move laterally. Basically, it stays in place. This water and its dissolved ions move up towards the drier region of the soil surface due to matrix potential. And if this water evaporates, it leaves behind precipitated salts, which in turn exert osmotic potential and draw even more water up from the groundwater reservoir. Irrigating, that is, adding even more salty water to the soil, raises the level of the groundwater table. If the water table gets high enough, salts, and especially sodium, will precipitate rapidly on the soil surface. This sodium flocculates the clay particles, causing soil sealing and making the soil practically impenetrable to water. Excessive salinity on the soil surface can eventually become so bad that plants can no longer grow, and the soil is permanently damaged. Fragments of ancient inscriptions describe endless fields of white soil in times of extreme salinity and famine. As centuries progressed, people eventually stopped growing wheat altogether in favor of barley, which is more salt-tolerant. Before the Islamic era, half-hearted management of the water table was the only real tactic for combating salinization. Eventually, when a tract of land became too saline to be cultivated, it was simply abandoned. However, a 10th century text by a scholar called Ibn Washiyya, a native of modern-day Iraq, attests to the fact that, by the Islamic Golden Age, theories of soil amendments had matured significantly. His text, called The Nabatean Agriculture, introduced, for perhaps the first time, the concept of soil types, namely alluvial, natric, and saline, like those found on the Mesopotamian plain, red clay, as might be found in Syria, and a variety of mountain soils, which could be found in the Zagros Mountains. His text put forth a number of new innovations in the realm of soil science. Among them, that glade soils could be identified by their aroma of sulfur, their bad acidic taste, or their affinity for black, violet, and dark green microorganisms when immersed in water for several weeks. That alkaline, saline soils could be managed with irrigation, but also the planting of specific crops that help remove salts by manuring or by mixing vine leaves and oil dregs into the soil. And also the concept of petrocalcic horizons, a diagnostic subsurface horizon which is basically accumulated calcium carbonates that have cemented into a hardpan. Ibn Washiyya recommended frequent plowing to break up the hardpan or prevent it from forming, trampling by animals, and manuring. To sum all that up, during the Bronze Age in Mesopotamia, amendments began and ended with irrigation, and also probably manuring when it came to managing the semi-arid saline soils of the river valley. However, by the Islamic Golden Age, soil science had made significant advances thanks to innovations by Islamic scholars. This culminated in Ibn Washiyya's monumental text, which classified soils according to their morphology and properties, and proposed amendments according to their classification. These amendments included irrigation and manuring, of course, but also plowing, trampling, and treatment with compost and oil. Oxisols are an order of soil defined as extremely old, extremely weathered, and dense in iron oxides and kaolinite. They are common throughout the tropics and are notable for their intense red hue. They're not especially fertile, and farming them is quite difficult. Prehistoric indigenous communities in the Amazon region developed a strategy to amend the Amazon oxisols, which was so effective that the soils they treated thousands of years ago are still rich and fertile to this day. These patches of deep, dark, nutrient-rich soil scattered throughout the Amazon basin are called terra preta. Essentially, terra preta is a type of anthropogenic soil formed between about 550 BC and 1450 AD by the addition of fire residues, namely charcoal and ash, as well as some other soil fertilizers like manure, fish bones, and biomass waste by indigenous agriculturalists. These soils are very fertile in comparison with untreated Amazon soils. Field experiments in the Amazon have shown that adding charcoal can increase soil productivity by up to 220%. Obviously, the effects of fire and fire residues on soil are major. Fire can directly influence soil properties through heating and combustion, and it can also indirectly influence the soil through vegetation changes and subsequent erosion. Fire is considered by some to be a seventh soil forming factor, in addition to the established six. The intensity of a fire determines the biological, chemical, and physical effects it will have on a soil. Below 200 degrees Celsius, most of the effects are biological. There will be destruction of microbial biomass, destruction of the seed bank, and destruction of fine root systems. Soil water repellency might be enhanced, as might aggregate stability. Above 200 degrees Celsius, though, chemical properties are affected. Organic matter is combusted, and pyrogenic organic compounds are produced. Soil pH goes up. Soil water repellency breaks down, as do the soil aggregates. Above 350 degrees Celsius, the clay fraction starts to fuse together. However, it's important to note that soils are bad conductors of heat. It would take a very intense fire burning for a very long time to produce the effects noted above. Additionally, heat penetration into lower horizons is very slow, and these effects usually only happen in the top few millimeters or centimeters of the soil. Really, the primary impact of fire on a soil is the destruction of the vegetation on the soil surface. Loss of vegetation certainly does make the soil more prone to erosion, but even more importantly, fire will also result in the deposition of ash, which is dense with nutrients and charred organic matter. This good stuff will mix into the soil via bioturbation or water infiltration and boost soil fertility. Furthermore, charcoal, pyrogenic organic matter, is more resistant to degradation and will persist in the soil for generations, for hundreds if not thousands of years. This charred material is sometimes fully charred, sometimes only partially charred, and this partially charred organic matter in particular has a porous structure that can retain water and nutrients very well. It also seems to boost the soil microbe population. Overall, controlled burns and ash treatments have made the terra preta soils huge carbon banks. The modern relevance of this tactic thus cannot be overstated. In the Netherlands and Germany, there are vast expanses of sandy, well-drained soils which don't retain much water or nutrients. They've historically been extremely difficult to farm. In the Middle Ages, farmers in these areas developed a method for amending this sandy, leachy soil. They cut turfs of sod, or ideally peat, from uncultivated land and gave them to their cows and sheep as bedding. After the bedding was saturated with manure, it was composted and then spread over the fields to add much-needed nutrients and to help with the soil texture. Over time, this created a very rich topsoil, about 2 meters deep, known as ploggen soil. This same method seems to have also been endemic to Scotland, as it was used by the invading Vikings after they settled down to become farmers in the 12th century. In fact, recent analyses of soils and middens in the Orkney Islands by Erica Gutman-Bond have shown that this method of composting has its roots in the Neolithic era. Neolithic and Bronze Age farmers in the Orkney Islands appear to have used the same sod cutting method, but rather than spreading the compost across a large field, they piled it into middens and plowed and cultivated the middens themselves. This is especially remarkable because sod composting lasted until at least the 1960s on many Scottish farms, which means that a Stone Age soil treatment was so effective that it remained in use until the 20th century.